Hello there, and welcome to this calm and soothing science for sleep channel. I'm truly glad that you've found your way to this video tonight, because together we'll be gently exploring some of the most fascinating and awe-inspiring wonders of the cosmos. Wherever you are in the world right now, whether you're resting in bed, sitting quietly in the dark, or simply taking a break from the noise of the day, allow yourself to slowly settle into this shared moment of stillness. Let your shoulders relax. Let your breathing deepen. Let the sounds of the world soften and fade into the background. As your thoughts begin to grow quiet, much like starlight slowly dimming as night becomes deeper and darker, imagine yourself drifting effortlessly through the vast night sky, weightless and calm, gliding past hidden planets tucked away in distant star systems, passing glowing stars that have burned steadily for billions of years, and floating alongside ancient galaxies whose light has traveled across unimaginable distances just to reach you in this moment. Tonight, we'll uncover gentle and fascinating truths about the universe, its mysteries, its quiet marvels, and the delicate, nearly invisible threads that connect everything you've ever known. Some of what you hear may softly surprise you, opening your mind to new ideas, while other discoveries will settle peacefully into your thoughts, resting there like distant light on a calm, clear evening horizon. And if these slow, peaceful explorations help you unwind, relax, or spark a sense of curiosity, you're welcome to like and subscribe. Doing so helps guide other tired minds and curious souls to this place as well, one sleepy listener at a time. But for now, there's nothing you need to do. Simply get comfortable, allow your breathing to slow, and let yourself drift as we begin this gentle journey through the cosmos. There are more stars in the universe than there are grains of sand on our entire planet. When you look up at the night sky, the countless stars twinkling above may already seem endless, scattered across the darkness in delicate patterns of light. Yet the reality is even more astounding than it appears. Scientists estimate that the total number of stars in the universe surpasses every grain of sand on all the beaches of Earth combined, from the longest shorelines to the smallest, hidden grains beneath the waves. Each of these stars is a blazing sphere of plasma, some far larger than our sun and others much smaller, each shining with its own intensity across unimaginable distances. Many of these stars have likely existed for billions of years, quietly illuminating their regions of space. Around countless stars, entire planetary systems may form, potentially hosting worlds that we have yet to imagine. This staggering abundance speaks to the vastness and complexity of the cosmos, reminding us just how immense and richly populated the universe truly is. A magnificent ocean of light and energy stretching far beyond the limits of human imagination. The observable universe itself stretches roughly 93 billion light-years wide, forming the portion of the cosmos we are able to see. This vast region contains all the galaxies, stars, planets, and matter whose light has had enough time to reach us since the very beginning of the universe. Yet, even this immense expanse may represent only a small fraction of what actually exists. Beyond this visible boundary, space likely continues endlessly, perhaps infinitely, filled with countless more galaxies, stars, and mysteries forever hidden from our view. The light from those distant regions simply hasn't had enough time to arrive yet, leaving them beyond our reach, wrapped in darkness and silence. This boundary of sight is not a physical edge or wall in space, but rather a gentle reminder of the limits of human observation and the vast unknown that still awaits discovery. Space itself is expanding, carrying galaxies farther apart with every passing moment. It isn't just that galaxies are moving through space. They are being carried apart by the expansion of space itself. This means the very fabric of the universe is stretching, slowly increasing the distance between galaxies over time. Imagine tiny dots drawn on the surface of a balloon. As the balloon inflates, the dots drift farther apart, not because they are moving on their own, but because the surface beneath them is expanding. In the same way, the universe continues to grow, shaping how light travels, how galaxies evolve, and what the future fate of the cosmos may be. This expansion is slow, steady, and relentless, quietly shaping the grand architecture of space and time. The Big Bang wasn't actually an explosion in space. It was the creation and expansion of spacetime itself. Often imagined as a massive blast, the Big Bang was far more profound. It was the moment when space and time came into existence. Before this event, there was no space to move through and no time to pass. Then, from a state of unimaginable density and heat, space began to expand and time started ticking forward, setting in motion the creation of everything we know. This early expansion wasn't a blast into empty space, but the rapid growth of all space itself, a concept that stretches the limits of our understanding and reminds us how mysterious the universe's origins truly are. Ancient light from the universe's earliest moments still fills every corner of space. The cosmic microwave background is a faint, nearly uniform glow of microwave radiation that surrounds us in every direction. This ancient light dates back nearly 14 billion years, to a time when the universe cooled enough for photons to travel freely without constant scattering. It is the leftover glow of the Big Bang, offering scientists a snapshot of the universe in its infancy. Subtle temperature variations within this radiation reveal the seeds of galaxies and the large-scale structure of the cosmos. Though invisible to our eyes, this ancient light quietly bathes us all the time, acting as a silent messenger from the dawn of time. Invisible matter forms a hidden framework that holds galaxies together. Dark matter, which neither emits nor absorbs light, makes up about 85% of the universe's total matter. This mysterious substance acts as an unseen scaffold, exerting gravitational pull that keeps galaxies and clusters from flying apart. Without dark matter, stars would drift away, and galaxies would struggle to form at all. Scientists detect dark matter only through its gravitational influence on visible matter and light. By mapping this invisible framework, astronomers gain deeper insight into the structure of the universe and the formation of vast cosmic webs. Despite being invisible, dark matter plays a fundamental role in shaping everything we observe. A mysterious force is also pushing the universe's expansion to speed up. After decades of assuming expansion was slowing, astronomers were surprised to discover that it is accelerating. This unexpected behavior is driven by dark energy, an unknown phenomenon that makes up nearly 70% of the universe's total energy content. Dark energy acts like a repulsive force, counteracting gravity and pushing galaxies farther apart over time. Its nature remains one of the greatest mysteries in modern physics, challenging scientists to rethink the fundamental laws of space and time. Understanding dark energy may ultimately reveal the fate of the cosmos itself. Galaxies are not scattered randomly. They are connected by vast webs of dark matter, forming an enormous cosmic network stretching across hundreds of millions of light-years. Along these filaments, galaxies cluster together, while immense voids, regions of near emptiness, lie between them. This cosmic web influences how galaxies grow, interact, and evolve over billions of years, revealing a universe that is delicately interconnected. The Milky Way spins at over 500,000 miles per hour, carrying our solar system along on an immense cosmic journey. Our galaxy is a sprawling spiral of stars, gas, and dust, rotating steadily as we orbit the galactic center once every 250 million years. This journey carries us through spiral arms filled with glowing nebulae and star clusters. Despite this incredible speed, the vast distances between stars make collisions extremely rare. This gentle motion reminds us how dynamic yet peaceful our place in the universe truly is. Sometimes, galaxies collide and merge in slow, majestic dances lasting billions of years. Galaxies are not static islands in space. They drift and interact under gravity's influence. When two galaxies come close enough, they begin a slow, graceful dance, eventually merging into a single, larger galaxy. These encounters can trigger intense bursts of star formation as clouds of gas compress and collapse, creating new stars and reshaping the cosmos. While stars themselves rarely collide directly during galactic encounters, the immense gravitational forces involved dramatically reshape the structure of entire galaxies. As galaxies pass through one another, gravity pulls and stretches their spiral arms, distorting their shapes and funneling vast clouds of gas and dust toward their centers. This inward flow of material can feed the growth of supermassive black holes lurking at galactic cores, allowing them to grow larger and more powerful over time. Even without stars crashing into each other, these slow cosmic interactions profoundly transform galaxies, altering their future paths across the universe. Our own Milky Way galaxy is part of this ongoing cosmic story. It is currently on a collision course with the nearby Andromeda galaxy, and in roughly 4 billion years, the two spirals will begin to merge. Rather than a violent crash, this will be a slow and graceful union lasting billions of years, eventually forming a new, larger galaxy, sometimes called a future cosmic city, filled with hundreds of billions of stars reshaped into a new structure. Quasars shine as some of the brightest beacons from the distant past, acting like brilliant lighthouses from the early universe. These extraordinary objects are found in the centers of young galaxies, shining across billions of light years of space. Powered by supermassive black holes that are actively consuming enormous amounts of gas and dust, quasars release staggering amounts of energy as material spirals inward and heats up. In many cases, a quasar can outshine its entire host galaxy, becoming visible across vast cosmic distances. This intense radiation allows astronomers to peer deep into the universe's early history, studying how black holes grew and how galaxies evolved when the universe was still young. Quasars illuminate the otherwise invisible intergalactic medium, revealing conditions that existed billions of years ago. Their dazzling brightness and incredible distances make them among the most fascinating and informative objects in the cosmos. In the universe's earliest moments, space itself expanded faster than the speed of light during an event known as cosmic inflation. Within a tiny fraction of a second after the Big Bang, the universe underwent this extraordinary burst of expansion, during which space expanded exponentially. This did not violate the laws of physics because it was space itself stretching, not objects moving through space. Inflation smoothed out irregularities, making the universe remarkably uniform on the largest scales. At the same time, tiny quantum fluctuations were stretched across vast distances, becoming the seeds of galaxies, clusters, and the large-scale structures we observe today. Inflation helps explain why the universe appears flat, uniform, and connected across enormous distances. It remains a cornerstone of modern cosmology, offering profound insight into the universe's earliest moments and its overall structure. The first stars ended the universe's long, dark silence, lighting up the cosmos for the very first time. For hundreds of millions of years after the Big Bang, the universe existed as a cold, dark expanse filled mostly with hydrogen and helium gas. There were no stars, no galaxies, and no sources of visible light. Then, gravity slowly gathered matter together until the first massive stars ignited. These ancient stars were enormous, incredibly bright, and short-lived, burning their fuel at astonishing rates. Inside their cores, they forged the first heavier elements, such as carbon and oxygen, elements essential for future planets and life. Their intense radiation began to reionize the surrounding hydrogen gas, clearing the cosmic fog and making space transparent to ultraviolet light. This transformative era, known as cosmic dawn, changed the universe forever, turning darkness into light and setting the stage for galaxies, planets, and eventually life itself. High-energy particles race through space at nearly the speed of light, born from the universe's most violent events. These particles, known as cosmic rays, are primarily protons and atomic nuclei accelerated to extreme energies by exploding stars, supernova remnants, and energetic regions around black holes. When these cosmic rays reach Earth, they collide with atoms in our atmosphere, producing cascading showers of secondary particles that spread through the air. Though invisible, cosmic rays constantly rain down upon our planet, subtly influencing atmospheric chemistry and potentially affecting cloud formation and climate. These energetic messengers link us directly to powerful events occurring far beyond our galaxy, quietly connecting Earth to the most extreme environments in the universe. Our galaxy belongs to a massive supercluster containing thousands of neighboring galaxies. The Milky Way is part of an enormous structure known as the Laniakea supercluster, a vast cosmic region stretching over hundreds of millions of light-years. Within this immense cosmic metropolis, thousands of galaxies move together under the influence of gravity. Galaxies within Laniakea interact, merge, and evolve, shaped by the combined gravitational pull of the entire supercluster. Understanding our place within this vast structure helps astronomers comprehend how matter is organized on the largest scales and how gravity shapes the universe over billions of years. Between galaxy clusters lie vast empty regions known as cosmic voids. These enormous spaces contain very few galaxies and have extremely low matter density. Some voids span tens of millions of light-years across, forming the quiet, empty regions between the bright filaments of the cosmic web. Although they appear nearly empty, voids still contain sparse gas and dark matter. Their presence plays an important role in shaping the large-scale structure of the universe and influencing how galaxies move and cluster around them. Studying cosmic voids provides valuable insight into dark energy, matter distribution, and the dynamics of cosmic expansion. Nearly invisible neutrinos pass through everything, including your own body, all the time. Neutrinos are tiny, nearly massless particles produced in vast numbers by the sun, exploding stars, nuclear reactions, and other energetic cosmic events. Because they interact so weakly with matter, neutrinos pass effortlessly through planets, stars, and even you without leaving a trace. Trillions of neutrinos pass through your body every second, silently connecting you to distant cosmic processes. Detecting these elusive particles requires enormous, highly sensitive detectors buried deep underground or beneath Antarctic ice. Despite their ghostly nature, neutrinos offer unique insights into stellar explosions, the sun's interior, and the fundamental laws of physics. On the largest scales, the universe looks remarkably uniform in every direction. When astronomers observe the cosmos across vast distances, they find no preferred direction or location. The distribution of galaxies appears the same no matter where we look. This large-scale uniformity, known as isotropy and homogeneity, forms a foundational assumption of modern cosmology. Observations of the cosmic microwave background strongly support this idea, revealing subtle patterns that hint at deep symmetries underlying the universe itself. A sea of ancient neutrinos fills space, relics from the earliest seconds after the Big Bang. Almost immediately after the universe was born, neutrinos decoupled from other matter and began streaming freely through space. These relic neutrinos form a cosmic neutrino background that still exists today. Unlike light, neutrinos pass through almost everything unimpeded, making them incredibly difficult to detect. Yet their presence influences how structures formed and evolved across cosmic history. Detecting this ancient neutrino background would offer a direct glimpse into the universe's earliest moments, fractions of a second after the Big Bang. Scientists measure the universe's expansion rate using a value called the Hubble constant. Since its birth, the universe has been expanding, and the Hubble constant describes how fast galaxies are moving away relative to their distance. It acts like a cosmic speedometer, helping astronomers estimate the universe's age, size, and future behavior. However, different measurement techniques currently yield slightly different results, creating what is known as the Hubble tension. Resolving this mystery could reshape our understanding of cosmology and the fundamental nature of space and time. As galaxies move away from us, their light stretches to longer, redder wavelengths in a phenomenon known as redshift. This stretching of light provides direct evidence of the universe's expansion and allows astronomers to measure vast cosmic distances. Redshift acts as a gentle cosmic signal, revealing how space itself continues to grow, carrying galaxies ever farther apart as the universe slowly evolves. As the universe continues to expand, galaxies are carried farther and farther away from us, drifting through space as the fabric of the cosmos itself stretches outward. As this happens, the light emitted by those distant galaxies is also stretched, shifting into longer, redder wavelengths in a process known as redshift. This effect is closely related to the Doppler effect we experience with sound, where the pitch of a siren drops as an ambulance moves away. In the cosmic version of this phenomenon, light waves lengthen as their source recedes through expanding space. Redshift not only serves as compelling evidence that the universe is expanding, but it also allows astronomers to measure how fast galaxies are moving away and how far they are from us. By carefully analyzing redshift, scientists can look deep into the past, reconstructing the history of cosmic expansion and tracing how the universe has evolved over billions of years, from its earliest moments to the vast structure we observe today. To measure the immense distances across the universe, Astronomers rely on a carefully constructed system known as the cosmic distance ladder. Measuring cosmic distances is extraordinarily challenging because stars and galaxies are far too distant to reach or measure directly. Instead, scientists use a sequence of overlapping methods, each calibrated by the one before it. The process begins with parallax, a subtle shift in a nearby star's position caused by Earth's orbit around the Sun. Once nearby distances are known, astronomers move outward using standard candles, objects such as Cepheid variable stars and certain types of supernovae whose true brightness is well understood. By comparing their known luminosity to how bright they appear, scientists can estimate their distance. This step-by-step ladder allows astronomers to map the scale of the universe with remarkable accuracy, revealing the size of galaxies, the spacing between clusters, and the timeline of cosmic evolution. The cosmic horizon marks the most distant boundary of the observable universe, defining the farthest regions we can ever see. Because the universe is approximately 13.8 billion years old, light from beyond a certain distance simply has not had enough time to reach us. This boundary forms a vast spherical region around Earth known as the observable universe. Beyond the cosmic horizon may lie countless galaxies, stars, and structures, but they remain hidden from view, forever beyond our observational reach. As time progresses, the horizon slowly expands, allowing light from slightly more distant regions to arrive. Even so, the cosmic horizon serves as a humbling reminder that our knowledge of the universe is inherently limited, inspiring both scientific curiosity and a deep sense of wonder. Drifting silently through space are tiny grains of cosmic dust, microscopic particles that play an essential role in shaping the universe. These grains are composed of elements such as carbon, silicon, and metals forged inside ancient stars. Though incredibly small, cosmic dust has an outsized influence on the universe's life cycle. In cold, dense clouds of gas and dust, these particles help radiate heat away, allowing gravity to pull matter together more efficiently. This cooling process enables clouds to collapse, giving birth to new stars. Around young stars, dust grains collide, stick together, and gradually grow into planets, moons, and asteroids. Dust grains also provide surfaces where complex molecules can form, laying the chemical groundwork essential for life itself. The universe's first stars were fundamentally different from the stars we see today. Formed from primordial clouds almost entirely composed of hydrogen and helium, these early stars contained virtually no heavier elements. Known as population 2 stars, they were massive, extremely hot, and intensely luminous. They burned through their fuel rapidly, living short but brilliant lives before ending in powerful supernova explosions. These explosions scattered the first heavy elements, such as carbon, oxygen, and iron, into space. Those elements became the building blocks for future generations of stars, planets, and eventually living organisms. Although none of these first stars survive today, their explosive deaths transformed the universe, setting the stage for its growing chemical complexity. Hidden behind thick veils of cosmic dust, many distant galaxies shine most brightly in infrared light. Dust clouds absorb visible light emitted by intense star formation, making these galaxies nearly invisible to optical telescopes. However, the absorbed energy is re-emitted at infrared wavelengths. By observing the universe in infrared light, astronomers can peer through these dusty regions and uncover galaxies undergoing rapid star formation. These dusty star-forming galaxies reveal critical chapters in the story of galaxy growth, helping scientists understand how galaxies evolved during the universe's early history. Cosmic rays, high-energy particles born from violent cosmic events, race through space at nearly the speed of light and may even influence Earth's atmosphere. These particles, mostly protons, are accelerated by supernova explosions and active galactic nuclei. When they strike Earth's atmosphere, they collide with atoms, creating cascades of secondary particles. Some researchers suggest that this ionization process could influence cloud formation, potentially affecting weather and climate. While the extent of this influence remains debated, cosmic rays provide a fascinating connection between distant cosmic violence and conditions on our own planet. Although the universe is dominated by matter, the near absence of antimatter remains one of the deepest mysteries in physics. According to theory, the Big Bang should have produced equal amounts of matter and antimatter, which annihilate upon contact. Yet somehow, matter came to dominate. This imbalance, known as baryon asymmetry, suggests unknown processes in the early universe favored matter's survival. Solving this mystery is essential to understanding why galaxies, stars, planets, and life itself exist at all. Gravity leaves subtle fingerprints on the ancient light that fills the universe. As light travels across cosmic distances, it passes near massive objects whose gravity bends and distorts its path, a phenomenon called gravitational lensing. These distortions leave faint imprints on the cosmic microwave background, the oldest light we can observe. By studying these patterns, astronomers can map the distribution of visible and dark matter, revealing the hidden structure of the universe. Gravitational lensing can also dramatically magnify distant galaxies, bending their light into arcs, rings, or multiple images. This natural magnification acts as a cosmic telescope, allowing scientists to observe objects otherwise too faint or distant. Because dark matter bends light without emitting any of its own, lensing provides one of the most powerful tools for uncovering its invisible presence. After hundreds of millions of years of darkness following the Big Bang, the universe's first stars ignited, marking the beginning of cosmic dawn. As these stars gathered into early galaxies, their combined light filled the cosmos for the first time. This ancient glow ended the cosmic dark ages and set into motion the processes that shaped galaxies, star clusters, planets, and ultimately life itself. The universe's first light was not merely illumination. It was the opening chapter of a complex and evolving cosmic story that continues to unfold today in its earliest years. The universe was not the clear, open expanse we see today, but a dense and fog-filled environment dominated by neutral hydrogen gas. This vast sea of hydrogen absorbed much of the light attempting to pass through it, leaving space dark and opaque. The birth of the first stars and galaxies marked a profound turning point. These early cosmic structures emitted intense ultraviolet radiation, energetic enough to strip electrons from hydrogen atoms, transforming the neutral gas into ionized plasma. This pivotal era, known as reionization, gradually cleared the cosmic fog. As hydrogen became ionized, light was finally able to travel freely across immense distances. The universe transitioned from a murky darkness into a transparent cosmos, opening a window through which the grand cosmic web of galaxies could eventually shine and be observed billions of years later. Billions of years after the Big Bang, the universe entered an extraordinary period of activity often called cosmic high noon. During this time, star formation reached its peak, with galaxies producing new stars at astonishing rates far greater than those seen today. This intense burst of stellar creation flooded the universe with energy and light while enriching it with heavier elements forged in stellar cores. As time passed, this frenetic pace slowed, and star formation gradually declined, giving rise to the calmer cosmic environment we now inhabit. This golden age played a defining role in shaping the universe's evolution, laying the structural and chemical foundation for galaxies, solar systems, and ultimately life itself. At the universe's birth, only the lightest elements, hydrogen and helium, existed, forged in the crucible of the Big Bang. Over time, stars acted as cosmic furnaces, fusing these simple elements into heavier ones such as carbon, oxygen, silicon, and iron. When massive stars reached the end of their lives and exploded as supernovae, they scattered these newly formed elements into surrounding space. This process enriched the interstellar medium, allowing future generations of stars and planets to form from increasingly complex material. Over billions of years, this continuous cycle of stellar birth, death, and rebirth transformed the universe from a simple primordial mixture into a chemically rich environment capable of supporting complex chemistry and life. On the largest scales, matter in the universe is arranged in an immense and intricate structure resembling a cosmic web. Enormous filaments of matter stretch across millions of light years, linking clusters of galaxies together like glowing threads. These filaments, composed primarily of dark matter and diffuse gas, form the backbone of the cosmos, guiding the motion and growth of galaxies along their lengths. Between these strands lie vast cosmic voids, enormous regions of near-empty space. Mapping this cosmic web reveals the universe's grand architecture and helps scientists understand how matter is distributed and how gravity sculpts the large-scale structure of the cosmos. At the hearts of many galaxies reside supermassive black holes, some of which unleash spectacular jets of charged particles traveling at nearly the speed of light. These powerful jets can extend for millions of light-years, blasting energy far beyond their host galaxies. As they interact with surrounding gas and dust, they can heat material, push it away, and even suppress or regulate star formation. By observing these energetic outflows, astronomers gain insight into the dynamic relationship between black holes and their galaxies, witnessing some of the most extreme and influential phenomena in the universe. Galaxy clusters represent the densest nodes of the cosmic web and are the largest gravitationally bound structures known. Each cluster can contain hundreds or even thousands of galaxies packed into regions spanning millions of light-years. Immense filaments of dark matter and gas funnel material into these clusters, drawing galaxies together through gravity. These regions are filled with extremely hot gas that emits X-rays, adding to their complexity and energetic nature. Studying galaxy clusters allows scientists to probe the distribution of matter on the largest scales and offers crucial clues about dark matter, dark energy, and the universe's long-term evolution. Remarkably, precise measurements reveal that the universe's overall geometry is extraordinarily close to flat. This means space does not curve inward like a sphere or outward like a saddle, but instead follows the rules of flat geometry even across cosmic distances. Such flatness implies a delicate balance between the universe's total energy and its expansion rate. This discovery strongly supports inflationary models of the early universe and suggests that cosmic expansion will continue indefinitely rather than reversing into a collapse. Understanding the universe's shape is essential for uncovering its origin, behavior, and ultimate fate. The cosmic microwave background radiation, the faint afterglow of the Big Bang, appears almost perfectly uniform. Yet hidden within it are tiny temperature differences, variations no greater than a few millionths of a degree. These minute fluctuations represent slight density differences in the infant universe. Over billions of years, gravity amplified these subtle irregularities, causing matter to clump together and form galaxies, clusters, and the vast cosmic web. These ancient ripples serve as the universe's original blueprint, preserving information about its earliest moments and the fundamental physics that governed its birth. In cosmology, some uncertainty is unavoidable because we observe only a single universe. This limitation, known as cosmic variance, arises from the fact that we cannot compare multiple universes to determine whether observed patterns are universal or simply the result of chance. As a result, statistical measurements of galaxy distributions or background radiation carry inherent uncertainties. This challenge forces astronomers to develop increasingly sophisticated models and analytical techniques. Cosmic variance reminds us that our perspective is unique and that even the most precise observations have fundamental limits. Scientists reconstruct cosmic history by measuring the ages of distant galaxies, effectively looking back through time. By analyzing the light from these galaxies and studying their stellar populations and spectra, astronomers can determine when stars formed and how galaxies evolved. Because light takes billions of years to reach us, observing distant galaxies reveals different epochs of the universe's past. These measurements help establish a timeline of cosmic events, from early star formation to chemical enrichment, painting a detailed picture of the universe's growth and transformation. Among the most intriguing theoretical ideas in cosmology are cosmic strings, hypothetical one-dimensional defects in spacetime predicted by some early universe models. These ultra-thin yet immensely dense filaments may have formed during phase transitions fractions of a second after the Big Bang. If they exist, cosmic strings could produce gravitational waves or leave subtle distortions in the cosmic microwave background. While no direct evidence has yet been found, the discovery of cosmic strings would revolutionize our understanding of fundamental physics and the universe's earliest moments. High-energy X-rays glow from distant regions where black holes devour surrounding matter, marking some of the most extreme environments in the cosmos. Deep within the hearts of many galaxies reside supermassive black holes, astonishing objects whose masses can reach millions or even billions of times that of our sun. These cosmic giants often remain quiet, hidden in darkness, but when gas and dust drift too close, gravity takes over. The infalling material forms a swirling accretion disk, spiraling inward at tremendous speeds. As particles collide and rub against one another, friction and immense gravitational forces heat the disk to millions of degrees. In these extreme conditions, vast amounts of energy are released in the form of powerful X-rays that can travel across billions of light-years. Space-based telescopes detect this radiation, allowing astronomers to observe violent processes unfolding near the black hole's event horizon. These glowing X-ray beacons reveal how black holes grow, how they influence their host galaxies, and how their energetic feedback shapes cosmic evolution. By studying them, scientists peer into some of the most extreme and mysterious environments the universe has to offer. Within galaxies themselves, turbulent clouds of gas play a central role in shaping star formation. These immense clouds are constantly stirred by gravity, shock waves from exploding stars, magnetic fields, and galactic rotation. Rather than remaining calm, the gas moves chaotically, forming eddies and currents that ripple through space. In certain regions, turbulence compresses the gas, creating dense pockets where gravity gains the upper hand. These collapsing regions ignite nuclear fusion, giving birth to new stars. The balance between turbulence and gravity determines how many stars form, how massive they become, and how long star formation can continue. This complex interplay of chaos and structure governs the life cycle of galaxies. Understanding these turbulent processes helps astronomers unravel how galaxies evolve and sustain star formation over billions of years, revealing the universe's vast and dynamic stellar nurseries. Across the cosmos, pulsars and distant galaxies continuously send out radio waves that fill space with an invisible symphony. Pulsars are rapidly spinning neutron stars, the dense remnants left behind after massive stars explode as supernovae. As they rotate, they emit narrow beams of radio waves that sweep through space like cosmic lighthouses. Alongside pulsars, entire galaxies emit diffuse radio radiation produced by energetic processes such as star formation, magnetic fields, and jets launched from supermassive black holes. Radio astronomy captures these faint signals, uncovering aspects of the universe hidden from optical telescopes. By listening to these radio emissions, scientists map magnetic fields, trace energetic particles, and explore large-scale cosmic structures. This unseen radio universe reveals a dynamic, energetic cosmos constantly alive with motion and activity. Exploding stars also hurl particles across the galaxy as cosmic rays. When massive stars reach the end of their lives, they erupt in supernova explosions that generate powerful shock waves. These shocks accelerate particles, mostly protons and atomic nuclei, to speeds approaching that of light. Once launched, cosmic rays travel vast distances through space, occasionally colliding with Earth's atmosphere. When they do, they create cascades of secondary particles that scientists can detect with ground-based instruments. These energetic visitors influence the chemistry and dynamics of interstellar space and may even play a subtle role in Earth's atmosphere. Cosmic rays serve as messengers from distant, violent cosmic events, directly linking our planet to some of the most powerful phenomena in the universe. Patterns hidden within the polarization of ancient light provide clues about the universe's earliest moments. The cosmic microwave background radiation, the faint afterglow of the Big Bang, is not only remarkably uniform but also subtly polarized. This polarization reveals how light waves oscillate in preferred directions, encoding information about density fluctuations and gravitational waves from the infant universe. By studying these delicate patterns, scientists test theories of cosmic inflation and trace how tiny quantum ripples grew into galaxies and clusters. These faint signals offer a rare glimpse into the physics of the universe's birth and the forces that shaped its large-scale structure. After the first stars formed, their intense ultraviolet radiation transformed the universe. Early space was filled with neutral hydrogen gas that absorbed light, making the cosmos foggy and opaque. Ultraviolet photons from young stars stripped electrons from hydrogen atoms in a process known as reionization. This cleared the cosmic haze, turning the universe transparent and allowing light to travel freely across immense distances. This transition opened the universe's windows, enabling galaxies and cosmic structures to be observed billions of years later and marking a crucial milestone in cosmic history. As the universe emerged from darkness, the first galaxies played a decisive role in this transformation. Their collective ultraviolet light ionized vast regions of hydrogen gas, permanently changing the universe from a neutral, fog-filled state into a luminous, transparent expanse. This reionization illuminated the cosmos for the first time and revealed the large-scale structure of galaxies. Studying this era helped scientists understand how the first luminous objects shaped the universe and laid the groundwork for the complex cosmic architecture we observe today. Despite gravity's pull, a mysterious force known as dark energy is causing the universe's expansion to accelerate. Dark energy acts like a repulsive pressure, pushing galaxies apart faster over time and accounting for roughly 70% of the universe's total energy content. Its nature remains one of the greatest mysteries in science. Whether dark energy will drive eternal expansion or lead to some unknown cosmic ending is still unclear. Unlocking its secrets is one of the central goals of modern cosmology. To describe how the universe grows, cosmologists use a concept called the scale factor. This dimensionless number tracks how distances between galaxies change over time. As the scale factor increases, space itself stretches, carrying galaxies farther apart. Measuring how this value evolves helps scientists reconstruct the universe's expansion history and understand the influence of dark energy. The scale factor provides a simple yet powerful framework for charting cosmic growth across billions of years. The universe's overall curvature also shapes its destiny. Depending on the total amount of matter and energy, the universe could be flat, open, or closed. Observations show it is astonishingly close to flat, meaning parallel lines remain parallel even across cosmic distances. This geometry supports current models of cosmic evolution and suggests continued expansion rather than eventual collapse. Curvature influences how light travels and how matter moves, guiding the universe's grand journey through time. On the largest scales, matter is distributed remarkably evenly. While galaxies cluster locally and vast voids exist, when viewed across hundreds of millions of light-years, matter appears uniform. This homogeneity supports the cosmological principle, which assumes the universe is both isotropic and homogeneous. These large-scale symmetries simplify our models and reveal fundamental rules governing cosmic evolution. Finally, cosmic isotropy means the universe looks nearly the same in every direction we observe. No matter where astronomers point their instruments, the large-scale properties of the cosmos remain consistent. This profound uniformity reflects deep underlying symmetries in nature and reinforces our understanding of the universe as a coherent, interconnected whole. Careful astronomical observations, including the most detailed studies of the cosmic microwave background radiation, reveal an extraordinary uniformity in temperature and matter distribution across the entire sky. No matter which direction scientists observe, the universe appears remarkably similar on the largest measurable scales. This quality, known as cosmic isotropy, suggests that the universe does not favor any particular direction or location. When isotropy is combined with homogeneity, the idea that matter is evenly distributed when viewed over vast cosmic distances, it forms the foundation of modern cosmology's understanding of the universe's large-scale structure. Together, these principles imply that the laws of physics and the fundamental cosmic conditions remain consistent throughout space, allowing scientists to construct universal models that describe cosmic history, expansion, and long-term evolution. These models help humanity understand not just where the universe is going, but how it came to be. The discovery of cosmic background radiation provided one of the most powerful confirmations of the Big Bang theory. In 1965, scientists Arno Penzias and Robert Wilson accidentally detected a faint, uniform microwave glow permeating the universe while working with sensitive radio antennas. This mysterious signal, now known as the cosmic microwave background radiation, turned out to be ancient light left over from the universe's earliest moments. This radiation is the afterglow of the Big Bang itself, dating back nearly 14 billion years to a time when the universe cooled enough to become transparent, allowing light to travel freely for the first time. Its discovery transformed cosmology from a largely theoretical pursuit into a precise scientific discipline. Detailed measurements of this ancient radiation revealed tiny temperature fluctuations, minute variations that served as the seeds from which galaxies, galaxy clusters, and vast cosmic structures eventually formed. Today, the cosmic microwave background remains a cornerstone of cosmology, acting as a time capsule from the universe's infancy and a guiding record of its evolution. Cosmic history spans an almost unimaginable range of time, from fractions of a second after the Big Bang to billions of years of gradual change. The universe's story began in an unimaginably brief instant known as the Planck epoch, occurring just a fraction of a second after the Big Bang, when the laws of physics as we know them were first taking shape. From this fiery beginning, cosmic history unfolded through a sequence of distinct epochs, including inflation, recombination, cosmic dawn, and galaxy formation. Each stage brought profound transformations. Space itself rapidly expanding, matter cooling and organizing, light emerging from darkness, and the first structures slowly forming. Over billions of years, galaxies evolved, stars ignited, planetary systems developed, and the universe grew increasingly complex. This immense timeline reveals a universe in constant motion and transformation, where every moment is connected, linking the distant past to the present and shaping the future in an ongoing cosmic dance. Understanding this timeline helps humanity grasp its place within the vast story of the cosmos. The observable universe continues to grow as the cosmic light horizon expands. This observable universe is bounded by the cosmic light horizon, which represents the farthest distance from which light has had time to reach us since the Big Bang. As time moves forward, this horizon slowly expands, allowing astronomers to observe ever more distant galaxies and cosmic structures. However, due to the ongoing expansion of space, some regions of the universe may remain forever beyond our reach. This expanding horizon defines the limits of human observation and knowledge, reminding us that while we have glimpsed incredible cosmic depths, much of the universe remains hidden in darkness, waiting patiently for future discoveries to broaden our understanding and sense of wonder. Brief yet extraordinarily powerful bursts of energy occasionally light up the universe. Gamma-ray bursts are intense flashes of high-energy radiation that can briefly outshine entire galaxies. Lasting from mere milliseconds to several minutes, these dramatic events often result from the collapse of massive stars or the violent merging of neutron stars. Despite their fleeting nature, gamma-ray bursts release enormous amounts of energy, illuminating distant regions of the cosmos. They act as cosmic beacons, offering vital clues about stellar death, black hole formation, and the universe's evolution. By studying these powerful flashes, scientists can probe extreme physical conditions that are impossible to recreate on Earth. As the universe expands, the very fabric of space stretches the light traveling through it. This stretching increases the wavelength of light, a phenomenon known as cosmological redshift. As a result, light from distant galaxies shifts toward the red end of the spectrum, making those galaxies appear redder than they originally emitted. Redshift serves as a cosmic clock, allowing astronomers to measure how fast galaxies are moving away and to estimate their vast distances. This effect provides direct evidence of the universe's expansion and enables scientists to look back in time, observing galaxies as they existed billions of years ago. The stretching of light is a subtle yet profound signature of cosmic growth. Relic neutrinos have filled space since the universe was only 1 second old. Almost immediately after the Big Bang, the universe was permeated by these tiny, nearly massless particles that rarely interact with matter. These relic neutrinos decoupled from the hot cosmic plasma within the first second and have streamed through space ever since. Though extremely difficult to detect due to their weak interactions, relic neutrinos influence cosmic evolution and the formation of large-scale structures. They serve as cosmic fossils, preserving information about the universe's earliest conditions. Detecting and studying them remains a major goal in physics, promising deeper insights into the universe's fundamental nature. Cosmic voids are vast, nearly empty regions stretching millions of light-years across, lying between dense galaxy clusters and filaments. These enormous voids resemble cosmic deserts, sharply contrasting with regions rich in galaxies and matter. Despite their emptiness, voids play an essential role in shaping the universe's large-scale structure by influencing gravitational forces and the motion of surrounding galaxies. Studying these voids helps scientists understand dark matter distribution, the effects of dark energy, and the evolution of cosmic architecture. These silent expanses highlight the delicate balance between matter and emptiness that defines the universe. Galaxies grow larger through slow, majestic mergers unfolding over billions of years. These dynamic systems evolve by gradually combining with neighboring galaxies, merging stars, gas, and dark matter into larger structures. Such mergers can trigger intense bursts of star formation, reshape galactic forms, and fuel central supermassive black holes. Our own Milky Way is expected to merge with the nearby Andromeda galaxy in several billion years. Understanding galactic mergers reveals how complexity builds over cosmic time, illustrating a universe in constant transformation. Invisible magnetic fields thread through galaxies, quietly guiding charged particles and shaping cosmic processes. Though far weaker than Earth's magnetic field, these galactic fields extend across thousands of light-years, influencing star formation, interstellar gas dynamics, and the motion of cosmic rays. Studying these unseen forces helps astronomers understand galactic behavior and the interplay between matter and energy on vast scales, adding further complexity to the cosmic tapestry. Cosmic rays, high-energy particles originating from supernovae and other extreme events, occasionally reach Earth. When they strike the atmosphere, they produce cascades of secondary particles, some of which penetrate living organisms. Occasionally, these particles cause mutations in DNA. While most mutations are harmless or repaired, some contribute to genetic diversity and evolution. This constant rain of cosmic rays links Earth's biological history to the wider universe, showing how cosmic events subtly influence life on our planet. In the universe's earliest moments, rapid phase transitions may have produced bubble-like structures in space-time. As these bubbles expanded and collided, they may have left detectable imprints in the cosmic microwave background or generated gravitational waves. These transitions relate to fundamental forces separating and symmetries breaking as the universe cooled. Detecting evidence of such bubbles would offer rare insight into high-energy physics and the conditions just after the Big Bang. Finally, tiny fluctuations in ancient light reveal the universe's beginnings. The cosmic microwave background contains faint ripples, minute temperature and density variations that became the seeds of all cosmic structures. Over billions of years, gravity amplified these subtle differences into galaxies, clusters, and vast cosmic filaments. By mapping these fluctuations with extraordinary precision, scientists uncover the universe's initial conditions and test cosmological models, allowing humanity to read the story of the cosmos written in its oldest light. These delicate imprints offer a profound and invaluable window into the universe's origins and the invisible forces that have shaped its evolution across billions of years. Subtle patterns preserved in ancient light and matter allow scientists to trace cosmic history back to its earliest moments, revealing how energy, gravity, and fundamental forces gradually sculpted the structure of the universe we observe today. Cosmic rays play a fascinating role in creating the northern and southern lights near Earth's polar regions. The dazzling auroras, known as the aurora borealis in the north and the aurora australis in the south, are partly sparked by cosmic rays, which are high-energy particles traveling vast distances through space. When these energetic particles collide with Earth's magnetic field and interact with the upper atmosphere near the poles, they excite atoms of oxygen and nitrogen. As these gases release energy, they glow in vivid shades of green, red, purple, and blue. Along with particles from the solar wind, cosmic rays energize the atmosphere, producing these shimmering curtains of light that ripple across polar skies. This remarkable connection between distant cosmic events and Earth's natural beauty reminds us that our planet is deeply embedded within a vast, dynamic universe, constantly shaped by subtle cosmic influences. Galaxies themselves flow along immense gravitational currents shaped by the universe's distribution of matter. Rather than drifting randomly through space, galaxies move along vast pathways defined largely by the presence of dark matter. These invisible gravitational flows guide galaxies along filaments of the cosmic web, pulling them toward dense clusters while skirting enormous voids. This continuous cosmic motion governs how galaxies form, interact, and evolve over billions of years. By studying these gravitational streams, astronomers can map the universe's large-scale structure and uncover the forces driving cosmic evolution, revealing the profound interconnectedness of matter on the grandest possible scales. Photons last scattered approximately 380,000 years after the Big Bang, marking a pivotal moment in cosmic history. As the universe expanded and cooled, it eventually became cool enough for electrons and protons to combine into neutral atoms. This event, known as recombination, allowed photons, particles of light, to decouple from matter and begin traveling freely through space. Before this moment, the universe was opaque, with light constantly scattering off charged particles. The release of these photons formed the cosmic microwave background radiation, the oldest light still observable today. This moment of last scattering transformed the universe into a transparent expanse, allowing light to journey across space and time. By studying this ancient radiation, scientists gain insight into the universe's earliest conditions and the framework upon which later cosmic structures developed. Small temperature variations within this ancient light went on to seed galaxies and clusters. Although the cosmic microwave background radiation is remarkably uniform, it contains incredibly tiny temperature differences, only millionths of a degree apart. These slight variations correspond to small density differences in the early universe. Over billions of years, gravity amplified these initial irregularities, causing matter to clump together and form galaxies, clusters, and the vast cosmic web. These primordial seeds laid the foundation for the universe's large-scale structure. By mapping these temperature fluctuations with extraordinary precision, scientists can peer back into the universe's infancy and better understand the processes that guided its evolution. Gravitational tides continue to stretch and shape galaxies over immense spans of time. Much like the moon's gravity creates tides on Earth, the gravitational pull of nearby galaxies and concentrations of dark matter produces tidal forces within galaxies themselves. These forces stretch, distort, and reshape galactic structures, influencing spiral arms, star formation regions, and overall morphology. Over millions and billions of years, tidal interactions can trigger bursts of star formation or even lead to full galactic mergers. Studying these tidal effects helps scientists understand how galaxies evolve within their cosmic neighborhoods and highlights the deeply interconnected and dynamic nature of the universe. Quantum fluctuations during cosmic inflation eventually grew into galaxies and clusters. During a brief but extraordinary period just after the Big Bang, the universe underwent rapid expansion known as inflation. During this time, tiny quantum fluctuations, minute variations in energy at the smallest scales, were stretched to cosmic proportions. Inflation magnified these subtle ripples, imprinting them onto the fabric of space-time itself. Over billions of years, gravity amplified these variations, transforming them into the rich cosmic structures observed today. This process elegantly links the quantum realm to the vast universe, revealing a deep connection between nature's smallest and largest scales. Cosmic dust grains serve as the seeds from which stars and planets are born. These microscopic particles, composed of elements such as carbon, silicon, and heavier metals, drift quietly through interstellar space. Though tiny, they play a crucial role in cooling gas clouds, allowing gravity to draw matter together. As these clouds collapse, new stars ignite, while surrounding dust forms spinning disks that can give rise to planets, moons, and other celestial bodies. Dust grains also enable complex chemical reactions, producing molecules essential for life. Despite their minuscule size, cosmic dust particles are fundamental building blocks of the universe's structure and diversity. Light years provide a way to measure distances far beyond ordinary human scales. A light year represents the distance light travels in 1 year, about 6 trillion miles or 10 trillion kilometers. This unit allows astronomers to describe vast separations between stars, galaxies, and cosmic structures. For example, the nearest star beyond our Sun lies more than 4 light-years away, meaning its light takes over 4 years to reach Earth. Light years connect distance and time, helping us comprehend the immense scale of the cosmos. The universe's oldest light has a temperature only a few degrees above absolute zero. The cosmic microwave background radiation permeates all of space at a temperature of about 2.7 degrees above absolute zero. This faint glow is the cooled remnant of the hot, dense early universe, stretched and chilled as space expanded over billions of years. Its nearly uniform temperature, punctuated by tiny fluctuations, carries the imprint of cosmic structure formation. This cold background reflects the universe's transformation from a fiery beginning to its current vast and tranquil state. Cosmic ray showers constantly cascade through Earth's atmosphere. When high-energy cosmic rays traveling near the speed of light strike atmospheric atoms, they generate cascades of secondary particles known as air showers. These particle cascades spread through the atmosphere and sometimes reach Earth's surface, where they are detected by instruments around the world. Cosmic ray showers provide valuable clues about extreme cosmic events such as supernova explosions and black hole jets. They also interact with atmospheric chemistry, subtly linking Earth to energetic processes across the universe. Cosmic voids influence the movement and growth of galaxies surrounding them. These immense regions, containing very few galaxies, exert gravitational effects that push matter outward, shaping the flow of galaxies along cosmic filaments. Voids play a crucial role in sculpting the cosmic web and offer insight into dark energy's influence on large-scale structure. Though seemingly empty, these regions quietly guide cosmic evolution. Jets from black holes sculpt their host galaxies. Supermassive black holes at galactic centers often launch powerful jets of charged particles moving near the speed of light. These jets can extend millions of light-years, heating surrounding gas and regulating star formation. Acting as cosmic sculptors, black hole jets shape galaxy growth and evolution. Observing them reveals the intricate relationship between black holes and the galaxies they inhabit. The first galaxies formed during a mysterious era known as cosmic dawn. Cosmic dawn represents one of the most transformative and awe-inspiring epochs in the entire history of the universe. It marks the moment when the first galaxies finally ignited after hundreds of millions of years of cosmic darkness. During this prolonged era of silence, the universe was filled mostly with cold, diffuse clouds of primordial hydrogen and helium gas. Slowly, under the relentless pull of gravity, these vast clouds began to collapse inward, growing denser and hotter over time. Within their cores, the very first stars were born, assembling into the earliest galaxies. These fledgling galaxies flooded the surrounding universe with intense ultraviolet radiation, triggering profound processes such as reionization that permanently altered the cosmic landscape. This luminous awakening ended the cosmic dark ages and opened a new chapter in which light could travel freely across space. Studying cosmic dawn allows scientists to understand how the universe transitioned from simplicity to complexity, revealing how the earliest building blocks evolved into the immense galaxies and structures that fill the sky today. It is a glimpse into the universe awakening from its long, silent slumber. The universe's oldest light continues to fill space almost perfectly uniformly. The cosmic microwave background radiation bathes the entire cosmos in a faint, omnipresent glow that dates back nearly 14 billion years. This ancient radiation is a relic from a time when the universe first became transparent, allowing light to move freely through space. Its remarkable uniformity is one of its most striking features, with temperature differences across the sky amounting to only tiny fractions of a degree. This near-perfect smoothness reflects the early universe's highly uniform state shortly after the Big Bang, before gravity had time to amplify minuscule irregularities into galaxies, clusters, and immense filaments. This subtle glow surrounds us in every direction, acting as a silent witness to the universe's infancy and serving as the foundation upon which all cosmic structure was later built. It is a vast cosmic backdrop that quietly connects humanity to the very origins of space and time. Measuring the ages of galaxies helps scientists chart the universe's long and intricate history. By studying the light from galaxies billions of light-years away, astronomers are effectively looking back in time, observing these systems as they existed in earlier cosmic eras. Detailed analysis of their spectra reveals the ages of the stars within them, indicating when star formation began and how it progressed over time. This form of cosmic archaeology allows researchers to reconstruct the timeline of galaxy growth, chemical enrichment, and the rise and fall of star formation rates. When combined with other observations, these measurements create a detailed portrait of cosmic history, showing how matter evolved from a hot, dense beginning into the richly structured universe we observe today. This method reveals the universe not as a static entity, but as an ever-changing system shaped by time, energy, and gravity. Cosmic evolution describes how everything in the universe changes over billions of years. It is the grand narrative of transformation that begins with the universe's fiery inception and continues through the formation of stars, galaxies, planets, and increasingly complex chemical structures. Over immense spans of time, fundamental forces shaped matter and energy, sculpting the cosmos into intricate and interconnected forms. Galaxies evolve, stars are born and die, and cosmic environments shift in response to internal and external influences. Understanding cosmic evolution provides perspective on humanity's place within this vast and dynamic universe, revealing a cosmos that is constantly growing, changing, and unfolding its secrets through time. Cosmic variance reminds us that we observe only one universe. This fundamental limitation in cosmology arises because scientists have access to just a single cosmic realization. Unlike laboratory experiments that can be repeated many times, astronomers must interpret data from one universe observed from one location within it. As a result, statistical measurements, such as fluctuations in the cosmic microwave background or the distribution of galaxies, carry unavoidable uncertainties. Some observed patterns may reflect chance variations rather than universal laws. Cosmic variance challenges researchers to carefully distinguish meaningful signals from random noise and highlights the unique vantage point humanity occupies while studying the cosmos. It is a humbling reminder of both our curiosity and our observational limits. Cosmic rays interact continuously with the solar wind flowing outward from the sun. The solar wind, a steady stream of charged particles emitted by our star, influences how many cosmic rays are able to reach Earth's atmosphere. This interaction modulates cosmic ray intensity, affecting ionization levels in the upper atmosphere and contributing to space weather phenomena. Changes in solar activity alter this balance, causing cosmic ray flux to rise and fall over the course of solar cycles. Understanding this complex relationship is essential for protecting satellites, astronauts, and modern technology from radiation damage. It also reveals how the sun acts as an intermediary between Earth and the broader cosmic environment. Magnetic fields stretch invisibly across entire galaxies, shaping their long-term evolution. Though unseen, these magnetic fields guide the motion of charged particles and influence the behavior of interstellar gas. They help regulate star formation by directing gas flows and affecting how clouds collapse to form new stars. Extending across thousands of light years, galactic magnetic fields interact with cosmic rays and plasma, adding layers of complexity to galactic dynamics. Despite being weaker than Earth's magnetic field, their enormous scale gives them a profound influence on how galaxies grow, maintain structure, and interact with their surroundings over billions of years. Reionization made the universe transparent to ultraviolet light. In the universe's early stages, neutral hydrogen gas absorbed energetic radiation, rendering space dark and opaque. As the first stars and galaxies formed, they emitted powerful ultraviolet light that ionized this hydrogen, stripping electrons from atoms and transforming the gas into a transparent plasma. This epoch of reionization lifted the cosmic fog, allowing light to travel freely across vast distances for the first time. This transformation permanently altered the universe's appearance and enabled the formation of the complex structures we observe today. Studying reionization reveals crucial information about the universe's first luminous objects and the processes that cleared the primordial haze. Cosmic dawn ultimately ended the universe's dark and opaque childhood. Before this era, the cosmos was filled with light-absorbing gas that prevented illumination from spreading. With the birth of the first stars and galaxies, intense radiation began clearing this fog, allowing light to permeate space and reveal the universe's structure. Exploring cosmic dawn helps astronomers understand the timing, mechanisms, and consequences of the universe's first illumination. Cosmic strings, if they exist, could reveal deep secrets of fundamental physics. These hypothetical, ultra-thin defects in spacetime are predicted by certain theories describing the universe's earliest moments. If real, they could stretch across enormous cosmic distances, subtly affecting gravity and potentially generating detectable gravitational waves. Discovering cosmic strings would provide profound insights into the nature of spacetime and the unification of fundamental forces, bridging the gap between quantum mechanics and cosmology. Inflation explains why the universe appears smooth and uniform on the largest scales. According to this theory, the universe underwent a brief period of extremely rapid expansion just after the Big Bang. This expansion smoothed out irregularities while spreading tiny quantum fluctuations across immense distances. These fluctuations later became the seeds of galaxies and large-scale structures. Inflation resolves several cosmic puzzles and remains central to modern cosmology, linking quantum physics with the universe's grandest structures. Photons from the Big Bang continue to carry messages from the universe's birth, silently traversing space and time, reminding us that the cosmos still whispers the story of its origins. Photons, the fundamental particles of light released during the Big Bang, have been traveling through the vastness of space for nearly 14 billion years, crossing unimaginable distances of expanding cosmic darkness to reach us today. These ancient photons now form what scientists call the cosmic microwave background radiation, a soft and nearly uniform glow that fills the entire universe in every direction. Though faint and invisible to human eyes, this background light surrounds us constantly, bathing all of space in a quiet afterglow of creation. The properties of these photons encode an extraordinary amount of information about the universe's earliest moments, revealing details about its original temperature, density, composition, and the processes that shaped its evolution over billions of years. By carefully studying these primordial photons, scientists are able to unlock secrets about cosmic origins, the brief but powerful period of inflation, and the formation of the first structures that would eventually become galaxies, clusters, and vast cosmic networks. These photons act as messengers from the dawn of time itself, carrying with them a direct connection to the universe's fiery beginning and allowing us to observe the echoes of creation still whispering through space. Cosmic rays were first discovered more than a century ago, marking one of humanity's earliest encounters with energetic particles arriving from beyond Earth. In the early 1900s, scientists noticed mysterious radiation penetrating Earth's atmosphere, passing through matter in ways that ordinary radiation could not easily explain. Through years of careful observation and experimentation, this radiation was eventually identified as cosmic rays, high-energy particles originating from outer space rather than from Earth itself. These energetic particles, consisting mostly of protons and atomic nuclei, travel at speeds approaching that of light and constantly bombard Earth from all directions, day and night. Early experiments conducted by Victor Hess and other pioneering researchers revealed that cosmic ray intensity increased at higher altitudes, a crucial discovery that confirmed their extraterrestrial origin. Today, cosmic rays continue to intrigue scientists, as they provide valuable clues about violent and energetic cosmic events such as supernova explosions, rapidly rotating neutron stars, and powerful jets launched from black holes. Their discovery marked the beginning of cosmic ray physics and permanently linked our planet to energetic processes unfolding across the immense scale of the universe. Cosmic horizons place fundamental limits on how far we can see into space and time. Because the universe has a finite age of approximately 13.8 billion years, light from beyond a certain distance simply has not had enough time to reach Earth. This boundary, known as the cosmic horizon, defines the edge of the observable universe and represents the furthest regions we can ever hope to observe directly. Beyond this horizon lies an unseen expanse of space and time, potentially filled with countless galaxies, structures, and mysteries forever hidden from our view. As the universe continues to age, this horizon slowly expands, allowing astronomers to observe objects that were once beyond our reach. However, due to the ongoing expansion of space itself, some regions may remain permanently unreachable, drifting away faster than light can travel. The cosmic horizon therefore sets a profound limit on human knowledge, reminding us that the universe is far vaster and richer than what observation alone can reveal. The cosmic microwave background captures a frozen snapshot of the universe in its youth. This ancient radiation is a faint, nearly uniform glow filling all of space, preserved from a time when the universe was only about 380,000 years old. At that moment, the cosmos cooled enough for charged particles to combine into neutral atoms, allowing photons to finally travel freely through space without constant scattering. This event created a lasting image of the universe's infancy, imprinted into the background radiation we still observe today. Within this radiation are subtle temperature fluctuations, tiny variations that reflect small differences in density present in the early universe. These minute variations served as the seeds from which galaxies, clusters, and the large-scale structure of the cosmos eventually formed. Detailed observations of the cosmic microwave background provide invaluable insights into the universe's age, composition, expansion rate, and overall evolution, making it a cornerstone of modern cosmology. Beyond temperature variations, ancient light also carries another layer of information known as polarization. The cosmic microwave background radiation exhibits subtle patterns in the orientation of its light waves, revealing details that temperature alone cannot provide. This polarization encodes information about gravitational waves and density fluctuations produced during the universe's earliest moments. By studying these delicate patterns, scientists are able to test competing models of cosmic inflation and better understand how tiny primordial fluctuations grew into galaxies and massive clusters over billions of years. Polarization measurements offer a unique window into the physics of the Big Bang itself, providing rare clues about the forces and conditions that shaped the universe at its very beginning. Cosmic filaments contain much of the universe's ordinary matter and define its vast large-scale structure. Galaxies are not randomly scattered through space, but instead cluster along enormous filaments composed of dark matter and ordinary, baryonic matter such as gas and dust. These cosmic filaments stretch across millions of light years, forming an intricate cosmic web that connects galaxies and clusters across the universe. While dark matter dominates the total mass, these filaments hold much of the ordinary matter that eventually forms stars, planets, and life. Much of this material exists as hot, diffuse gas flowing between galaxies, making it difficult to observe directly. By studying these filaments, scientists can trace how matter moves through the cosmos and how galaxies grow and evolve within this immense interconnected network. Jets from black holes can stretch for millions of light years, ranking among the most powerful structures in the universe. Supermassive black holes located at the centers of galaxies often launch narrow jets of charged particles that travel at nearly the speed of light. These jets can extend far beyond their host galaxies, sculpting the intergalactic medium and dramatically influencing their surroundings. By heating and displacing gas, these jets regulate galaxy evolution, sometimes suppressing star formation and other times triggering new bursts of stellar birth. Observing these colossal jets provides insight into the powerful relationship between black holes and their cosmic environments, revealing some of the universe's most energetic and dynamic processes. Inflation left subtle imprints on the ancient light we detect today. During a brief but extraordinary moment of cosmic inflation, the universe expanded exponentially, stretching tiny quantum fluctuations to macroscopic scales. These fluctuations became the seeds of all cosmic structures, including galaxies, clusters, and vast filaments. The imprint of inflation remains encoded within the cosmic microwave background radiation as delicate patterns of temperature and polarization variations. By studying these subtle imprints, scientists gain insight into the universe's earliest instant and the physical laws that governed its rapid birth, linking the smallest quantum processes to the largest structures in the cosmos. Inflation's legacy links the quantum world with the vast cosmos, revealing a profound unity between nature's smallest and largest scales. In the earliest fraction of a second after the Big Bang, tiny quantum fluctuations, variations smaller than atoms, were stretched across the universe by rapid cosmic inflation. These microscopic ripples eventually grew into galaxies, clusters, and immense cosmic structures, demonstrating how the universe's grand architecture is rooted in the behavior of particles at the smallest imaginable scales. This connection reminds us that the same fundamental laws govern both the invisible quantum realm and the breathtaking immensity of the cosmos, weaving all of existence into a single, unified story. Cosmic rays may also play a subtle role in Earth's cloud formation and climate. Some scientists propose that cosmic rays influence Earth's atmosphere by affecting the formation of clouds high above the planet's surface. When cosmic rays enter Earth's atmosphere, they collide with air molecules, ionizing them and creating charged particles. These charged particles can act as microscopic seeds around which cloud droplets begin to form. Clouds, in turn, play a critical role in regulating Earth's temperature by reflecting incoming sunlight back into space, while also trapping heat near the surface. Although the precise extent of this effect remains an active area of scientific debate, cosmic rays offer a fascinating link between distant cosmic events and Earth's delicate climate system. This possibility highlights the intricate and fragile interplay between outer space and the environment that sustains life on our planet. Galactic movements follow paths set by immense cosmic filaments. Galaxies do not drift randomly through space, but instead move along vast gravitational currents defined by the filaments of the cosmic web. These enormous strands of dark matter and gas act like invisible highways, guiding galaxies toward dense clusters and away from enormous voids. Over billions of years, this steady flow shapes galaxy interactions, mergers, and long-term evolution, gradually forming the large-scale structure of the universe we observe today. Mapping these cosmic highways allows astronomers to better understand the hidden forces sculpting the universe's architecture and reveals how matter moves and evolves across incomprehensible distances and timescales. Neutrinos offer rare and powerful clues about the universe's very beginnings. Neutrinos are tiny, nearly massless particles produced in staggering numbers during the universe's earliest moments, just seconds after the Big Bang. These elusive particles decoupled from matter almost immediately and have been streaming through space virtually unhindered ever since, passing effortlessly through stars, planets, and even our own bodies. Although extremely difficult to detect, relic neutrinos carry invaluable information about the universe's infancy, fundamental physical laws, and particle interactions at energies far beyond what human-made experiments can achieve. Studying neutrinos allows scientists to probe conditions otherwise inaccessible, opening a unique window into the origin of the cosmos and the forces that govern it. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the dazzling brilliance of newborn stars to the silent shadows of ancient galaxies resting at the edge of time. From the intricate web of dark matter shaping the universe to the faint whispers of cosmic background light echoing from the dawn of creation, you have traveled through glowing star nurseries, soared along luminous spiral arms, and glimpsed the universe's heart softly shining across unimaginable distances. You are part of this cosmic story, not merely an observer, but a participant woven into the fabric of stardust and time itself. The atoms within your body were forged in the fiery cores of ancient stars that lived and died long before Earth was born. The air you breathe carries the legacy of distant explosions that scattered life-giving elements across space. Everything within you shares a deep lineage with the universe, born from the same primordial matter that now flows through galaxies and drifts silently in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming in hidden nebulae. Light continues its endless journey across space. Cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well, rest deeply, and dream softly beneath the gentle glow of the universe. Good night.